Okay, so let's go over a couple things here. I first want to go over the Oxenham and Bacon article, give you a little example. So you have intensity on this axis here. You have like basilar membrane vibration on this axis here. But so the Oxenham and Bacon article talks about how the outer hair cells act as a amplifier and a compressor, basically. And what they do, so as intensity rises, so as the intensity of a sound gets higher, in lower intensities they act in a linear way. And then at some point, once the intensity gets to a certain level, it starts to compress. Okay? So at this point, you have nonlinear behavior. Okay? So up to here, you have your input equals your output. Okay? After, we call this a knee point. You'll talk about this in hearing aids. This is how hearing aids work. Once you get to a certain point, an intensity for outer hair cells starts to become compressive nonlinear. So outer hair cells basically increase, they act more strongly for low-level sounds, and they compress mid to high-level sounds. And that allows us to hear a wide dynamic range from very low level to higher level sounds. Okay? So that's how the outer hair cells work. A linear input-output function, so as intensity increases, your basilar membrane vibration goes up at the same amount. So this would be linear. This would be essentially a non-linear function. Okay. Hearing aids have a processing algorithm called compression. Okay. In particular, wide dynamic range compression. We call it WDRC, wide dynamic range compression. Okay, so I want you to look that up. But wide dynamic range compression acts like the outer hair cells. Basically tries to mimic what they normally do. So wide dynamic range compression is used to treat sensorineural loss. So people with sensorineural hearing loss need a lot of boost here in this low-level sounds. But because of recruitment, or an abnormal growth of loudness, as we'll talk about, they need less gain as the sound gets louder. And that's what the outer hair cells do naturally. So wide dynamic range compression, when we talk about loudness perception, we'll bring this up again. Okay? But that's how outer hair cells work. All right, now I want to go over the lab. So hold on, I need to adjust this screen a little bit. So a couple things. These are the three sounds I sent you. The long signal, the 8000K, which should say 8000 hertz long signal, or 8K, and then the short signal. All right. So I wanted to show you when we talk about sampling frequency and the number of samples in a signal. So I created, I think these are both 1000 hertz tones. This one's just very short compared to the others. But if we take this and zoom in a little bit, you can see the sampled points. Now down here in project rate, this is sampling frequency. So if you remember, I said we can go up to like 384,000 samples per second. We don't really need to do that. It could be overkill, but typically this is about what we use. 44,100, 44K, 44.1K is what we call it. And that can, according to your Nyquist, get you out to about 22,000 hertz. Okay, so that's why a lot of people use it. But you can see the options. All right, so let me zoom in a little bit, and you'll be able to see the sampled points, which are there. So remember, they're discrete points in time. You can see that, right? So this is a digital signal because there are discrete points in time. This isn't 8,000 hertz sampling frequency. This is a 44 100 hertz sampling frequency. And you can see there's a lot more sampled points in the 44K than the 8K. All right. And then this is a 44K, but just very short in its duration. Okay. So there you can see sampling frequency. This is a sampled point here, and there's an amplitude value associated with it. So the bit resolution, remember, tells you how many values, potential values these can take. So you have sampling frequency, how many you have, and then amplitude quantization, bit resolution. It tells you the number of values you can take. Okay, and I'm going to have you look up, even though you haven't had a hearing aids class, we're going to talk about a particular hearing aid and how it uses various amplitude quantization or bit resolution values. So hopefully that helps you understand sampling frequency. I'm going to do this, and I'm going to play, actually no, I'm not going to do that yet. I'm going to highlight some of this, and I'm going to go to, you can't see it up top, but analyze plot spectrum. And I'm going to show you here how all of the energy essentially is concentrated at one. Let me do this first. Let me get a longer segment there. So here's a long signal, analyze plot spectrum. And here you can see that you have all of your energy at one point. So you remember the visual in the lens textbook where we had those little side lobes. So you can see for this sound, you can see that almost all of the energy is focused at one. So it's 1,000 hertz, I think. Yeah, it's about 1,000 hertz. Now, this signal's so short here, it's really hard. You can't get the same analysis, but I wanted to show you just for visualization purposes. So this is a short signal, very short, but it's still 1,000 hertz. If you go analyze plot spectrum, can't use the same analysis parameters, but I wanted you to see that you have a broader. Now this is because of the analysis parameter, but if we were able to do this if we had the ability to use the same analysis parameter, what you would see is with, hold on, let me get a pen here. Where is my, I don't know why I can't get my pen. It's usually down here. In either case, if you were using the same analysis parameters and this software would allow you to do it, you would see a broader spectrum for this very short sound with those side lobes like you saw in the lens text than you would see with this longer sound. Okay, so that shows the effective duration on the frequency spectrum. Now I want you to hear, let's see. Let's listen to the long signal. Okay. Now let's listen to the short signal. So it's not going to sound like 1,000 hertz because it's very short and has a broader frequency spectrum. So here's what it's going to sound like. So you hear that little almost like click noise, and it doesn't sound like 1,000 hertz. So when signals are very short, they lose that original property. They have broader spectral energy. All right, so let's listen again. And if you were to use a different program where you could measure this, you would have a broader spectrum. Even though this is 1,000 hertz, just like this one and this one, it would have different frequency characteristics. So very short sounds have broader spectral characteristics, even if they're created using the same mechanism here and here. And again, I wanted you to see sampling frequency. So the 8,000 hertz has many, many fewer than the 44K versus the 96K. And again, you could go up to 384,000, 384K, just because you can. Now remember, there's an inverse relationship between storage, not an inverse. There's a relationship between storage, data storage, and sampling frequency. The more samples you use, the more storage you need. And so there are limitations. Like I mentioned, everything in digital signal processing has a trade-off. Okay. And what I'm going to have you do is I'm going to have you look up Widex, WIDEX. So I want you to Google Widex music program, okay, or Widex and music, okay, because I'm going to go over how, and I think I mentioned this yesterday, that as you increase the bit resolution, so as you are able to apply more values to the amplitudes, you're able to get a wider dynamic range of inputs without distortion. And so I want you to look at that, because Widex has a good program, has a good processing system for music. It doesn't distort music and make it sound awful like some other products do, okay? And so we'll talk about that. So again, I wanted to touch on outer hair cell function. Wide dynamic range compression, WDRC, is a hearing aid processing system that we'll talk more about. But the WDRC is designed to basically do what the outer hair cells do when the outer hair cells are damaged, which is what are damaged with everybody who has sensory neural hearing loss, And so we'll chat more about that as well. All right, I hope this was helpful, and I will be in touch with you.